A fundamental problem in information theory is compressing information in the most efficient manner. Given some data that we draw from a probability distribution, we want to find the simplest representation possible while also minimizing information loss. The most intuitive way to do this is by exploiting the structure of the data's distribution. If we know what patterns are common or uncommon, we can structure our compression such that common patterns are compressed to a simpler representation than uncommon patterns. Behind this is what I think is the most beautiful concept in information theory and the topic of this video, the asymptotic equipartition property. In this video, my goal is to give you an intuitive and visual understanding of the AEP starting from first principles, along with discussing the important proofs necessary to understand it. To start, it would be good to understand the concept of entropy in information theory. There are a plethora of resources on this, and a good one is the video by the YouTuber 3Blue1Brown, which I've linked below. It is most important to understand that entropy is nothing more than the expected information of a random variable, where information is the negative log of the probability of an event. It would also be good to briefly recap the weak law of large numbers. Long story short, the weak law tells us that the sample average of IID random variables becomes increasingly likely to be close to their expected value as the number of samples grows. More formally, for any epsilon greater than 0 and delta greater than 0, there exists some capital N such that, for every n greater than capital N, the sample average is within epsilon of the expected value with probability 1 minus delta. Let us begin by considering the problem of drawing a sequence of n symbols from a discrete memoryless source. Each symbol can be one of k choices, where k is referred to as the alphabet size. The probability of seeing this sequence is nothing more than the product of the probability of seeing the first symbol times the probability of seeing the second symbol, and so on. But how informative is this sequence? Recall that the information of an event is given by the negative log of its probability, which lets us turn this product into a sum. What if, instead of the total information of the sequence, we wanted to see how informative each symbol was on average? We could divide by n to find the average information per symbol. Now, a natural question to ask is what happens as n goes to infinity? Luckily, we can use the weak law of large numbers to analyze this. The weak law tells us that with more and more draws, the average information of a sequence from the source distribution will converge to the expected information of the source. And the expected information is nothing more than the entropy. This is the key statement of the AEP that we will use throughout the rest of this video, and it boils down to this. The average information per symbol converges to the expected information. Keep this sentence in mind because it leads to some surprising consequences. Practically, our sequences will not be infinitely long, and we will choose a finite n. At these finite sequence lengths, the average information will differ wildly across sequences. For example, high probability sequences will have minimal information, while low probability sequences will have more. However, to compress as effectively as possible, we'd like to examine sequences that have information around the entropy. If we set some tiny value epsilon, and we find a sequence with information within an epsilon distance of the entropy, we can call this sequence epsilon typical. Sequences that are epsilon typical make up what is called the typical set. The size of the typical set is tiny compared to the size of the set of all possible sequences, but the majority of the probability mass is found within the typical set. Intuitively, this says that the probability mass mostly comes from sequences with average information close to the entropy. By the weak law of large numbers, we know that for a sufficiently large n, the probability a sequence is epsilon typical can be made arbitrarily close to 1. To find the probability of an epsilon typical sequence, we can split the absolute value in the previous inequality. Adding the entropy, multiplying by negative n, and exponentiating gives us the following inequality. With epsilon small, this means that all typical sequences have about the same probability, that is about 2 to the negative n times the entropy. This is where the equipartition comes from. The probability mass is almost uniformly partitioned across typical sequences as n gets large. This can sometimes lead to counterintuitive examples. For starters, the most probable sequence is not always in the typical set, since its information can be much less than the entropy. Sequences more likely to be in the typical set usually have symbols distributed similarly to the source distribution. For example, flipping a biased coin with 90% heads n times would give a typical set of sequences with around 90% of the symbols showing heads and around 10% of them showing tails. It would likely not include sequences with higher probability, such as the all heads sequence. As a consequence of the AEP, We know that as the sequence length gets longer, the probability of an arbitrary sequence from the source distribution landing in the typical set goes to 1. However, paradoxically, the cardinality of the typical set becomes a smaller proportion of the total set of sequences. This can be seen by analyzing the cardinality of the typical set. We start with the identity that the sum of the probability of all sequences adds up to 1. Obviously, this sum is lower bounded by the sum of the probability of all epsilon typical sequences. We previously saw that the probability of an epsilon typical sequence is lower bounded by this decaying exponential term. We can then replace the sum with the cardinality of the typical set. This gives us that the cardinality of the typical set is upper bounded by 2 to the power n times the entropy plus epsilon. A similar proof I've omitted here shows us that the cardinality of the typical set is lower bounded by the following term. The full proof can be found in the description and follows a similar method. If we assume again that the value of epsilon is small, we can approximate the cardinality as about 2 to the power n times the entropy. Dividing this by the size of the set of all sequences gives us a term that decays exponentially in the sequence length, showing that the typical set makes up a smaller proportion of the total set of sequences as sequence length increases. There is one notable exception to all that we have talked about. For a uniform distribution over k symbols, each sequence has the same probability of 1 over k to the power n, and the entropy of the distribution is log k. Taking the average information per symbol will always give log k, meaning that every sequence is in the typical set, and the probability of a sequence being in the typical set is 1. This can be seen by plugging in the entropy as log k, and seeing that the ratio of the cardinality of the typical set to the set of all sequences is 1. Now that we've discussed the AEP and typicality, we can apply these techniques to compression by developing a simple yet effective compression scheme. The setup here is simple. We draw a sequence of n symbols from a memoryless source, and we want to compress this sequence into a smaller sequence of m bits, called a code word, such that our decompressor can reconstruct the original sequence. We will start by using our notion of typicality to divide the set of all possible sequences into the typical set and atypical set. Since we know the typical set is small compared to the atypical set, but its sequences make up most of the probability mass, we can exploit this for compression. Let's start by giving an integer index to each of the sequences in the typical and atypical set. It doesn't matter exactly how we do this, but a natural way is to use lexicographic order. It is known that any integer can be represented in bits using 1 plus its log base 2, and that the size of the typical set is at most size 2 to the power n times the entropy plus epsilon, so it will require no more than n times the entropy plus epsilon plus 1 bits to compress the typical sequences. The atypical set is at most size k to the power n, so it will require no more than n log k plus 1 bits to compress atypical sequences. To compress a sequence, we can simply convert the index for each sequence into a binary string. To differentiate between the sequences that are typical and atypical, we can add a flag bit of 0 at the beginning of all the typical sequences and 1 at the beginning of all the atypical sequences. This would help the decoder to know where to look when converting from the index to the full length end sequence. This scheme has many nice properties. Firstly, the encoder is injective, meaning that no two different sequences can be compressed to the same code word. Secondly, we are able to compress the typical sequences to very small lengths, which is important because they are the most likely to be drawn. We can quantify how good this scheme is with its average code word length, which is the expected value of a code word's length over all code words. This gives us a sum over all sequences of the probability of a sequence times its code word length. We can simplify this expectation by splitting into two sums for the typical and atypical sequences. We can then upper bound the code word length for the typical set sum using our previous result, plus an extra bit for the flag bit. We can then do the same for the atypical set sum. The sums can then be simplified to the probability that an arbitrary sequence is typical or atypical. We saw previously that the probability of an arbitrary sequence from the source distribution being epsilon typical can be made arbitrarily close to 1, so we can upper bound the probability of a sequence being typical as 1 and the probability of a sequence being atypical as an arbitrary delta. This gives us a final bound on the average code word length. If we divide this quantity by n, we get the average number of compressed bits per source symbol, called the compression rate. This converges to the entropy as n goes to infinity, and this is significant because the entropy of a source is the theoretical limit of compression as proved by Shannon. Since so much real-world data contains statistical patterns that we can exploit, the basic intuition behind the AEP appears in many real-world applications. It is extremely important for the theory behind data compression, source coding, and channel coding. For more resources on the AEP, please check out the description below. Thank you for watching.